Hello, I'm Walid Dachraoui from the Electron Microscopy Center of Empa, the Swiss Federal Laboratories for Material Science and Technology in Dubendorf, Switzerland. Today I would talk to you about the use of liquid cell TEM to investigate phenomena at the anode electrolyte interface in lithium-ion battery. My talk will start with the motivation about the challenges at the anode electrolyte interface, and then I will show you the methods and techniques used for our in situ experiments and the STEM imaging techniques, of course. After that, I will give you some details about our study of the lithium dendrites and the dead lithium formation mechanisms, and I will finish with a short conclusion. A typical lithium-ion battery is composed of a negative electrode and a positive electrode and the electrolyte allowing the connection between them. During charge, lithium migrates from the positive electrode to the negative electrode, and during discharge, the opposite way occurs. The electrons are circulating in the same time at the external circuit, and if we look close at the negative electrode interface with the electrolyte during charge, when the lithium is transported with the solvent molecules get inserted to the negative electrode, these molecules are reduced, and then we have formation of a layer called the solid electrolyte interface. If we keep going down in the potential, we have also formation of lithium dendrites, and during discharge, these lithium dendrites can dissolute and form dead lithium. All these processes and mechanisms that happen at the anode electrolyte interface are very important for the safety and the workability and the efficiency of the battery. For that, it's important to understand and study their formation mechanisms. However, the SCI and the lithium dendrites are air sensitive, fragile, and occur locally with the fast growth and dissolutions kinetics. For these reasons, the preparation and transport of the sample can generate damages and modification of the initial properties of the SCI and lithium metals, which render post-mortem characterization non-efficient. For that, using in situ operando characterization with high spatio-temporal resolution will be the best way to characterize or to study the mechanism of their formations. Here, we are using in situ electrochemical liquid cell STEM technique. The in situ setup we are using in our study is the Poseidon 510 holder from Protochips. This holder allows the encapsulation of liquid between two microchips. The first microchip is a spacer microchip where we have spacers at the corner to control the thickness of liquid, and the second microchip is called electrochemical microchip where we have electrodes. Here we can see the counter electrode and the reference electrode and the working electrode is in the middle at the silicon nitride membrane window where we can image using the electron beam. To build the cell on top of the holder, it's simple by aligning the two microchips on top of each other, and with the help of gasket O-ring, liquid can be encapsulated and sealed from the vacuum of the electron microscope. After that, we can inject liquid and then we can cycle the battery inside the TM. Here you can see the complete setup where we have the cell inside the TM, the electron beam pass through the silicon nitride windows, and then we can image the interface between the working electrode and the electrolyte. The electrolyte can be injected using a syringe pump, and then the potentiostat to control the electrochemistry cycling of the microbattery. So for our imaging, we are using the Z contrast imaging technique called high angle annular dark field STEM, where the contrast of the generated image is related to the Z of the element forming this sample. For example, here in this image, the bismuth lead appears brighter than the iron with lower Z, and this technique of imaging is easy for interpretation and also easy the control of electron dose. First, as routine of our experimental measurements, it's very important to optimize the experimental conditions and control the scan rate, the flow rate, check the electrolyte connection, and the electron beam effect on the electrochemical and the electrolyte. Here we have the scan rate optimized, the liquid flow rate also, and we checked the electrolyte connection and the resistivity at the interface using the impedance spectroscopy. The electron beam effect on the electrochemistry with the beam off and the beam on is tested, and also we used the electron dose or optimized the electron dose to make it possible to image the electrolyte without any secondary effect. Here are the parameters chosen for our experimental or our experiment for solid electrolyte interface growth and lithium dendrites. The electron dose here and the flow rate 2.5 microliter per minute, and the scan rate is 100 millivolt per second. The first thing we did for our experimental part, we injected the electrolyte first, and here is the CV of cycling. We can see that we have a decomposition of the electrolyte corresponding to the solid electrolyte interface, and we can see that the growth of the SEI is basically based on nanoparticles growth, and the first cycle allow formation of an incomplete SEI layer. This will allow a further contact between the electrolyte and the electrode or the anode. If we continue going to lower potential during cycling, a large peak corresponding to the lithium electrodeposition appears. The STEM images here show the nucleation and the growth of the lithium dendrites, The growth initiate with the nucleation of lithium clusters first, as you can see here, and after that nanoparticles of lithium grow. These nanoparticles grow in size, and then after that we have a phase of lithium dendrites formation where we have the lithium will deposit beneath the nanoparticles, pushing them away from the anode to the electrolyte. And we can see that the width of the tip of the lithium dendrites still or keep constant, which means that we have a root growth based formation of the lithium dendrites, and after that we can see that branches start to form at the tip of the lithium whiskers. So if we take a look on the working electrode using optical microscopes to see the charge process, we can see that we have solid electrolyte interface formation, and then after that we have growth of lithium dendrites, and surprisingly we have long dendrites with a lot of branches formed, allowing the formation or allowing a dendritic structure of lithium dendrites. The question here, if only the root growth is the responsible of the growth of lithium dendrites, how does this leads to the formation of dendritic lithium dendrites? So here, if we go back to our STEM images and focus on one of those lithium dendrites with this inverted contrast, we can see clearly a shell of black contrast surrounding the lithium whiskers. This can be considered as a secondary SEI layer. This layer is thinning over cycling until cracks and holes appears where a new branch of lithium start to be formed via a tip growth. And this can explain how the transition from root growth to tip growth, allowing the formation of dendritic lithium dendrites. Here is a schematic illustration of showing the detailed mechanism of the growth based on the previous observations. We have to keep in mind the plating is basically based on meeting between the electrons and lithium ions to form lithium metal. First, lithium ions can meet electrons at certain position or certain positions beneath the solid electrolyte, and then this will allow the formation of nanoparticles, and these nanoparticles grow in size with a continued plating, and then after that the lithium metal will start depositing beneath these nanoparticles, pushing them away to the electrolyte, and the SEI is protecting these lithium dendrites until cracks can form after a stretching of this solid electrolyte interface. And in these positions, electrons coming through the lithium metals can meet again the lithium ions, and then we have formation of branches via a new deposition or plating of lithium metals. And here we can see that the solid electrolyte interface play a crucial role or an important role to make a combination between the root growth and the tip growth to allow the formation of dendritic lithium dendrites. During discharge of the battery, we can see that in the CV we have another peak of lithium dissolution, and This corresponding to the dissolution of lithium dendrites. And from this movie, we can see that the dissolution is incomplete. We start with the complete lithium dendrites, and then we have thinning until we have some lithium metals which are not involved in the reaction anymore, means that they are disconnected from the electrodes. Here is a typical lithium dendrite where we studied the thickness of this LE dendrite uh, in the bottom and in the middle and at the tip, and we found that we have homogeneous thinning until we have detachment from the bottom, and this can be explained with these curves, that the bottom is thinner than the tip initially, and during the thinning the bottom will detach or shrink before the tip, and this will make the rest of the lithium metals electrochemically inactive or disconnected from the electrode, and with that we have formation of dead lithium. So here we have three typical lithium dendrites undergoing dissolution. The first one is undergoing uniform shrinking, where we have shrinking everywhere in different sites uniformly, and this allowing the detachment at the end of 30% of the metal. And the second one and the third one are non-uniform shrinking, where, for example, in the first one we have some cracks or regions where we don't have the solid electrolyte interface, and in these regions there are detachment of lithium metals until we have detachment at the end from the root, and we have around 50% of the initial lithium metals became inactive metal. The third and the last one is allowing a special shrinking, where we have formation of islands, and we have different species of dead lithium formed until we have a disconnection or detachment of the lithium metal from the root, and we have also around 52% of the initial lithium metals became inactive metals. So here is a schematic illustration of the mechanism of dissolution of lithium dendrites. The lithium dendrite is surrounded by the solid electrolyte interface. In the first case, we have complete thinning of the solid electrolyte interface, and the thinning will be in different or all over the lithium dendrite, and we have homogeneous shrinkage until we have detachment, and there are dead lithium formations. The second case, we have a partial shrinkage where we have some parts having cracks in the solid electrolyte interface, and then we have lithium dendrites or lithium dissolution from these sites until we have detachment. And the third case, we have island-like shrinkage, where we have shrinkage or dissolution allowing the formation of lithium metal species until the detachment and the connection, and all these examples or mechanism allowing at the end the formation of dead lithium metals with different amounts. So here we came to uh, understand or to conclude that the partial dissolution is the driving force behind formation of dead lithium. With this, we came to the conclusion. I want to say that electrochemical liquid cell TM is a powerful tool to study complex mechanism inside a lithium-ion battery. Using this method, we were able to study the growth of solid electrolyte interface, and to show that lithium dendrites growth is a multi-step process, starting with the growth of nanoparticles, and then the root growth allow the formation of dendrites, and then after that the solid electrolyte interface plays a role on switching from root growth to tip growth, and then we have dendritic lithium shape. During the discharge process, we found that the thinning and the shape of the lithium dendrites are two parameters allowing the formation of dead lithium. And with that, uh, we found that we have different amount of dead lithium formed with different mechanisms. If you want to know more about this study, you can go to our publication in Nano Energy here. And I want to thank our group of electron microscopy center at Empa, headed by Ernie Rolf, and group of materials for energy conversion at Empa, especially Corsin Battaglia and Ruben Köhner. Thank you for following this talk, and if you have any questions, please contact me via my email shown here.